Welcome back to the Deep Dive, the place where we take complex, often dense technical material and turn it into actionable, fascinating insights. Today, we're undertaking a deep dive into supervised learning, specifically focusing on classification techniques. And these represent three fundamentally different philosophical approaches to problem solving. We're moving well beyond the simpler models, the perceptrons and the single decision trees, that might form the foundation of your knowledge.
That's right. Our goal is to provide you, the listener, with a shortcut to understanding the mechanics, the advantages, and, crucially, the trade-offs of 5 powerhouse algorithms. These span across 3 categories: the local instance-based approach of k-nearest neighbors, the combined power of ensembles like bagging, random forest, and boosting, and then the deceptively simple probabilistic framework of naive Bayes.
Okay, before we jump into the algorithms themselves, let's quickly anchor ourselves. Just a quick recap on supervised learning, just to set the stage. What's the fundamental mission here?
Supervised learning, fundamentally, it's all about learning a mapping function. So you have a known training set of input-output pairs. We usually call the input $6, that might be a vector of features, and the output dollars, which is the target variable. The algorithm's job, its mission, is basically to look at these pairs and generate a function that can accurately predict the dollars for any brand new, unseen test example, $6.
Right. And the distinction that drives our entire discussion today is really about the nature of dollars.
Exactly. If that target output dollars is continuous, a real valued variable like predicting housing prices or maybe temperature, that's regression. But today, our focus is on the world where $dollars is discrete. So if $dollars falls into distinct categories like, is this email spam or not spam, or classifying an image as a cat or a dog, that's classification.
And we often classify algorithms based on how they learn. We've talked about tree models before, maybe functional models like support vector machines. But the algorithms in our sources today fall into some really distinct new categories.
Yeah, our deep dive will focus on 2 major distinctions that fundamentally change how the learning process works. First, we have lazy learners, and KNN is the classic example there. Second, we have ensemble methods, which are strategies for combining multiple Bayes learners to get, hopefully, superior results. And finally, we'll look at naive Bayes, which is a really powerful example of a probabilistic classifier.
Okay, let's start with k-nearest neighbors, or KNN. It's famously categorized as a lazy learning algorithm. That word lazy, it sounds almost negative, but it actually describes a really radical philosophical difference, doesn't it? What does it mean for KNN to be lazy?
Yeah, the term lazy is purely technical here, and it's absolutely crucial for understanding the algorithm. You see, most classification algorithms are what we call eager learners. They take the training data and they immediately build an explicit model like a decision tree, or they figure out a hyperplane or a set of weights before they ever see a single test point. KNN does. Well, it does basically no explicit model training whatsoever. It literally just waits until a new test record comes along to do all its heavy lifting, all the computation.
Okay, so if it's not building some mathematical structure, if it's not fitting weights or defining parameters ahead of time, what is the model then? How does it know what to do?
That's the key insight, and this is where the philosophy just completely diverges. The model, quote unquote, is the entire training data set itself. It's just stored. Classification is then based entirely on calculating similarity on the fly, right when it's needed, to its neighbors. It's also categorized as a non-parametric learning algorithm. What that means is its complexity isn't fixed by some set number of parameters. It adapts completely to the size and the shape of the data. And this adaptability, well, it's strength, but also, as we'll definitely get into, its biggest weakness when it comes to resources.
Right. So to make this system work, given that it's not really learning weights or anything beforehand, it relies entirely on this idea of similarity. What are the 3 foundational things KNN absolutely needs to classify anything?
Okay, 3 essentials. First, you absolutely must have the full set of stored records. That's the training data itself, just sitting there. Second, you need a predetermined distance metric. You have to decide how you're going to measure similarity or closeness between any 2 records. And third, you have to pick the value of Tollebrock. That little letter K specifies exactly how many of the nearest neighbors you're going to look at to make the final decision.
Got it. So an unknown record comes in. Walk us through the mechanics then. How does this lazy approach actually spit out a classification?
Right. So when an unknown record enters the system, the algorithm finally kicks into gear and does all the work. It computes the distance from this new point dollar to every single point stored in the training data, every single one. Then it sorts all those calculated distances to identify the dollar data points that are closest. Now, for classification, which is our focus, we use a kind of voting system. It just assigns the majority class label found among those taller nearest neighbors. And just as a side note, if you were using KNN for regression instead, it would typically assign the average response value of those dollar neighbor.
Okay, that distance metric is clearly the engine driving KNN. For typical data, real valued continuous features like someone's height and weight, what are the standard ways to measure closeness?
Yeah, the most common, kind of the default metric for real valued features is the Euclidean distance. You might also hear it called the Dewey-2 norm. It's basically just the simple straight line distance you learned about in geometry, calculated as the square root of the sum of the squared differences between the feature coordinates.
But I know there's another common one too, the Manhattan distance, or L-1 norm. Why do we usually default to Euclidean, the tool Dewey-2? Is there a specific reason?
Ah, that's a great technical point. Yeah, the Manhattan distance, L-1, it sums the absolute differences. Think of it like calculating distance if you could only travel along grid lines, like walking blocks in Manhattan. Now, while the 1 is sometimes useful because it's less sensitive to outliers, but Euclidean metric is generally preferred. Why? Because it creates a smoother, more mathematically convenient distance space. That squaring operation in tool Dewey-2 naturally emphasizes the bigger differences more dramatically, which usually helps distinguish close neighbors from really distant ones more effectively.
Makes sense. And since this whole algorithm hinges entirely on measuring features, I imagine you really need to trap the input data carefully, right?
Oh, absolutely. Feature scaling is basically mandatory for KNN. Think about it. If you have two features, say income measured in tens of thousands, and age maybe from 0 to 100, that income feature, just because its numbers are so much bigger, will completely dominate the distance calculation. Age will barely have an impact. So to prevent this, you must normalize or standardize all your real valued features. The goal is to get them onto a similar scale so they contribute more or less equally to the distance calculation.
Okay, good point. And what about discrete features? Things like color maybe, or yes-no attributes. How do we measure distance there?
Right. For discrete features, we switch gears. We typically use the Hamming distance. This metric is pretty simple. It just counts the number of positions where the corresponding symbols in two strings or vectors are different. So if you have red, yes, large, and blue, yes, large, the Hamming distance is 1 because only the first feature is different. It's a really effective way to measure similarity in that kind of categorical space. And critically, the sources also mention you can assign weights to features when computing distance. This allows you, maybe through expert knowledge, to say, hey, this feature is way more important, and give it more influence in the similarity calculation compared to less important ones.
Okay, now we get to the really crucial hyperparameter. The choice of dollars. This seems like it determines everything. What happens if we pick a really small dollar, like the simplest case? What does the decision boundary look like then?
If is very small, the algorithm becomes hyper-local. It's only looking at the single closest point. The decision boundary becomes incredibly complex and jagged. The 1NN boundary, for instance, essentially maps out something called a Voronoi diagram. Basically, every point in the space gets classified according to the label of its single nearest training point. You get these very sharp, angular boundaries between classes.
And what's the big danger of having a boundary that's that complex?
The main danger is high variance. The boundary becomes extremely sensitive to individual training points, and that includes any noisy or maybe even mislabeled data points you might have. If a single outlier happens to be the nearest neighbor to a new test point, bam, the classification is wrong. This high sensitivity means a small dollar leads to a really high potential for overfitting the training data. It learns the noise, not just the signal.
Okay, so if small dollars is noisy and leads to overfitting, why wouldn't we just crank dollar way up, make it a really large number, maybe half the size of the entire training set? Wouldn't that guarantee a nice, smooth, generalized decision boundary?
That's a very logical thought process because increasing dollar definitely smooths out the boundaries and reduces that variance problem we just talked about. However, setting a dollar too large introduces the opposite kind of error. Bias. If your neighborhood, the group of tall points you're considering, becomes too expansive, it might start including points that actually belong to other classes, even if your test point is deep inside its own cluster. The classifier then ends up averaging across these different classes, which leads to inaccurate predictions. It starts to underfit the underlying pattern because it's smoothing things out too much.
Yeah.
So yeah, selecting dollars, it's that classic bias variance trade-off in action. Finding the sweet spot is key.
Right. Okay, let's try and consolidate the pros and cons of this whole lazy approach. Its non-parametric nature sounds really appealing.
It really is. The main advantage is its simplicity, conceptually, and its adaptability. It's super easy to update with new data. You literally just add the new points to your stored data, and boom, the model is instantly updated and ready. And it works excellently when your data has naturally well-defined, maybe nonlinear clustering structures, where points of the same class are just physically close together.
Mm-hmm. But the cost of being lazy has to be paid somewhere, right? In KNN, it seems like it's paid during the prediction phase.
Exactly. That's the kicker. The classification of a new record is computationally expensive, very expensive. This means the algorithm is fundamentally slow at prediction time. That full distance calculation and then sorting across the entire training set has to happen for every single query.
Wow, okay. And what about its performance when faced with modern data sets, the ones that might have thousands or even tens of thousands of features? How does it hold up?
That brings us to its major limitation, the dreaded curse of dimensionality. KNN generally performs poorly on datasets with very high dimensionality. The reason is, in high-dimensional space, data becomes incredibly sparse. Points that might seem close together if you only looked at two features could actually be very, very far apart when you consider them across hundreds or thousands of features. This sparsity really messes with the reliability and even the meaning of our distance metrics. The whole concept of a nearest neighbor becomes kind of ambiguous. So KNN works best in relatively low-dimensional spaces where local density is actually meaningful.
Okay, that transition from KNN's issues with high variance and dimensionality brings us perfectly to ensemble techniques. These seem designed specifically to overcome the limitations of single learners. The philosophy here sounds really powerful. If one classifier is decent, a whole committee of them should be better, right?
Absolutely. The core philosophy is about aggregating diversity and reducing error. We use many classifiers, often called base learners or weak learners, and we combine their results into a sort of super classifier. And this isn't just about getting a tiny improvement. Ensembles often provide a really significant, sometimes even dramatic, boost in accuracy. They consistently achieve lower generalization error compared to pretty much any single model you could build on its own.
So to create this necessary diversity among the different base learners, because if they all make the same mistakes, combining them doesn't help ensembles rely on one really essential process, bootstrap sampling. We probably need to understand exactly how that works first.
Right. Bootstrap sampling is absolutely fundamental to many ensemble methods, especially bagging and random forests. It's a statistical technique. What you do is you draw a sample uniformly at random with replacement from your original training data. So if your original training set has non-Dalibé points, your bootstrap sample will also contain exactly null points.
Okay, but the key there is with replacement. So the resulting data set isn't identical to the original one, is it?
Precisely. Because you're sampling with replacement, some of the original data points will likely be selected more than once in the bootstrap sample. And conversely, some original points won't be selected at all. On average, statistically speaking, any given bootstrap sample will contain about 63.2% of the unique original training points. Some points get picked multiple times, and roughly a third of the original data, these are often called the out-of-bag samples, get left out entirely for that particular sample. This random perturbation, this jiggling of the training data for each base learner you train, is what guarantees the necessary diversity and helps make the learners more independent.
Got it. Okay, let's examine the first major technique that uses this, bagging. That's short for bootstrap aggregation, right? How does it work?
Bagging is conceptually pretty straightforward. First, we create multiple bootstrap samples from the original training data, maybe hundreds or thousands of them. Then we fit many base classifiers to these different resampled versions of the data. Usually for bagging, we use large, complex decision trees, the kind that are prone to overfitting, the ones with high variance. We typically don't prune them, or maybe we prune them just a little using the original training data as validation. And importantly, we train each of these trees independently and often in parallel.
Okay, so you've got hundreds of potentially slightly different high variance trees. How do you get the final prediction out of that collection?
We just aggregate the results. For classification, we use a simple, unweighted majority vote. Whichever class gets predicted most often across all the trees wins. If we were doing regression, we typically just average the predictions from all the individual trees. The really great benefit of bagging is that it significantly reduces the overall misclassification rate. By averaging out the high variance, the noise sensitivity of those individual complex trees, you end up with a much more stable and accurate overall prediction. The errors tend to cancel each other out.
Right, averaging out the noise. Okay, now let's move to the algorithm that really kind of revolutionized ensemble methods. Random forest. This is often called a refinement or a fancier version of bagging. What's the fundamental difference that elevates it beyond standard bagging?
The elevation, the key refinement, comes from adding an additional calculated layer of randomness. Sometimes it's called feature bagging. See, standard bagging only randomizes the data that each tree gets to see via the bootstrap samples. Random forest goes a step further. It uses a modified tree learning algorithm. When the algorithm is deciding on the best way to split a node in the tree, it doesn't even look at all the available features to find the very best split. Instead, at each candidate split, it selects only a random subset of the features to evaluate.
Wow, okay, so we're deliberately restricting the algorithm's choices at each step.
Yeah.
Is there a typical rule of thumb for how big that random subset of features should be?
Yeah, there are some common heuristics that work well in practice. If you have total features in your data set for classification tasks, the algorithm often only considers about the square root of the total number at each split. Or sometimes another common choice is the base 2 logarithm of so log or polar features. It's a much smaller number than the total $2.
But why? Why introduce this restriction?
Right.
If you happen to have a really, really strong predictive feature, why would you deliberately hide it from the splitting process sometimes? Seems counterintuitive.
But that's the genius move. It's specifically designed to combat correlation between the trees and the ensemble. Imagine you have a data set where, say, 99 features are pretty weak predictors, but one feature, let's call it F$11, is just overwhelmingly strong. It predicts the outcome really well. In standard bagging, what happens? Nearly every single tree you grow, regardless of the specific bootstrap sample it saw, is going to select that super strong feature F$1 as the very first split, right near the root of the tree. The result: you end up with an ensemble of hundreds of trees that all look remarkably similar, especially at the top. They're highly correlated.
Right. If all the trees are making similar predictions, especially similar errors, averaging them doesn't help as much. Correlated errors don't average out effectively.
Exactly. That's the problem. When the trees are highly correlated, the ensemble's overall prediction error doesn't drop nearly as much as it could or should. Random forest fixes this. By forcing the algorithm to randomly ignore that super strong predictor F$1 at many of the splits, it gives other, maybe weaker, features a chance to be selected for the split, especially higher up in the tree. This promotes much greater diversity among the trees. It ensures the individual base learners are much more independent of each other. And that independence, that lack of correlation, is the true source of the ensemble's power boost over simple bagging.
Okay, that makes a lot of sense. So random forest tackles the high variance problem inherent in single decision trees, and it does it even more effectively than standard bagging by actively reducing the correlation among its base learners. So what are the costs? What are the trade-offs associated with this really robust performance?
Well, there are definitely trade-offs. Random forests are known for being highly accurate and consistently achieving lower generalization error than single trees or even standard bagging. That's the big plus. But they become dramatically less interpretable. You can't just easily look at a random forest and trace a single path down one tree to understand why a particular decision was made. It's a black box, essentially. Furthermore, they are more computationally expensive to build and run, simply because you're building potentially hundreds or thousands of these modified trees. However, they do provide a really invaluable side benefit: a reliable estimate of feature importance. Because features are randomly left out, you can measure how much the prediction accuracy drops when a particular feature isn't available across all the trees. This gives you a good sense of which features are actually driving the predictions.
Interesting. Okay, let's move to our third major ensemble technique: boosting. If bagging and random forest focused on creating independent learners, often in parallel, mainly to reduce variance, how does boosting differ conceptually?
Boosting takes a fundamentally different approach. It's an adaptive, sequential technique, and its core philosophy is focused primarily on reducing bias rather than just variance, although it often reduces variance too. So instead of training lots of parallel, complex trees independently, like in bagging or random forest, boosting fits trees sequentially, one after the other. And the key difference, the core idea, is that it adaptively weights the observations in the training set for each subsequent learner.
Adaptively weights. That sounds like some kind of continuous error correction process. How does that sequential weighting work in practice? What's it actually doing?
It's essentially an iterative focusing mechanism. You grow the first tree on the original data, then you look at where that first tree made mistakes. When you go to grow the second tree, the algorithm intentionally focuses more intensely on the data points that were misclassified or had large errors from the preceding tree or the combination of all preceding trees. Those difficult points, The ones the model got wrong are assigned higher weights. This forces the next tree being built to pay closer attention to them and try harder to get them right. If you look at more advanced versions like gradient boosting, the subsequent trees aren't even trying to predict the original outcome directly. Instead, they're trained to predict the error, the difference between the actual dollars and the prediction made by the current ensemble up to that point.
Wow, okay, that is a fundamental difference. So bagging is like gathering this massive committee where everyone gets trained on slightly different data and then they all vote equally. Boosting sounds more like an apprenticeship, where the master constantly points out the apprentice's mistakes from the last attempt, forcing them to specifically learn from those past errors in the next round.
That's a fantastic analogy. It really captures that sequential, error-correcting nature. And here's another structural detail that highlights the bias reduction focus. Unlike bagging, where large, complex, high-variance trees are often favored in boosting algorithms like AdaBoost, adaptive boosting, or gradient boosting, the standard best practice is actually to grow small, shallow trees. Often they're just stumps trees with only a single split. These are very weak learners individually.
Wait, small trees, weak learners. If boosting is all about improving accuracy, why on earth would you use weak learners as the base?
It seems counterintuitive, right? But the power in boosting comes from the sequence and the aggregation, not from the strength of any individual component. Small, weak trees like stumps have high bias. They can't capture complex patterns on their own, but very low variance. They aren't sensitive to noise. By fitting hundreds or even thousands of these weak learners sequentially, where each new tree focuses on correcting the residual errors left by the aggregate of all the trees before it, you manage to drastically reduce the overall bias of the final ensemble without dramatically increasing its variance. The final prediction in boosting isn't usually a simple majority vote like in bagging. It's typically a weighted majority vote or a weighted sum. Trees that perform better, meaning they reduce the overall error or residuals more effectively during their stage of training, are given greater influence in the final combined prediction.
Okay, that's a really crucial distinction. So if we synthesize these two main ensemble approaches, bagging, and random forest as a refinement, is largely a parallel variance reduction method, often using strong, complex base learners. Boosting, on the other hand, is a sequential bias reduction method, typically using weak, simple base learners. That's a critical difference for listeners to grasp when deciding which ensemble technique might be appropriate for their problem.
Exactly. Variance reduction versus bias reduction, parallel versus sequential, strong learners versus weak learners. Those are the key philosophical divides.
All right, moving on from the collective intelligence of ensembles, we're going to pivot now to an entirely different philosophy, the probabilistic approach embodied by the Naive Bayes classifier. This model, as the name suggests, is founded entirely on Bayes' theorem.
That's right. Naive Bayes is fundamentally a probabilistic classifier. It tries to model the relationship between the features of your data and the class memberships using conditional probabilities. In the context of classification, what we're really trying to compute is the posterior probability, that is, the probability of a specific class given the observed features of our data point.
And the mathematical expression we're trying to maximize to make our decision is P text features.
Text
features, is that right?
Exactly. Our goal is to find the class C dollars that makes that whole output value the largest. Now, that numerator has two important parts. There's the likelihood P text features, which asks, if we assume this class is true, what's the probability of observing this specific set of features? And there's the prior probability, P text class, which is simply how common that class is in our training data overall before we even look at the features.
Okay, now let's address the elephant in the room. That word naive. That isn't just some stylistic choice, right? It refers to the foundational, defining, and arguably problematic characteristic of this algorithm.
Yes, the naive part is absolutely central. It refers directly to the strong independence assumption the algorithm makes. What naive Bayes assumes is that, given the class, each of the attributes or features are conditionally independent of each other. So in simple terms, if you know an object is, say, a dog, the algorithm assumes that the probability of it having long legs is completely independent of the probability of it having brown fur, given that it's a dog.
Which, in the real world, is often not true. Features are frequently correlated. Long legs might be more common in certain breeds, which also tend to have brown fur, for example.
Precisely. But calculating the true joint probability text features without making that independence assumption would be computationally, well, a nightmare, especially if you have many features. It would become intractable very quickly. You'd need an absolutely enormous amount of training data to reliably estimate the probability for every possible combination of feature values. So The naive assumption is essentially the computational shortcut. It allows that complex joint probability calculation to simplify dramatically. It just becomes a product of the individual conditional probabilities. PC MathBFX becomes proportional to multiplied by the product of PC for every feature dollar. And multiplying probabilities is way, way easier than calculating that massive joint probability. This simplification is what makes naive Bayes so incredibly efficient.
Okay, but as you said, features in the real world, things like height and weight, or maybe certain behavioral attributes are almost always correlated to some degree. That means the independence assumption is very often violated in practice.
That's the critical point of friction, absolutely. In reality, that core assumption often breaks down, sometimes quite severely.
So, despite this known flaw, let's walk through the implementation. In the training phase, how does the algorithm actually learn the pieces it needs?
The training phase for naive Bayes is remarkably simple and incredibly fast. It basically involves learning two things from the training data. First, the prior probabilities, PCA, for each class, that's just counting, what percentage of the training examples belong to Class A, Class B, etc. Second, it needs the conditional likelihoods for every feature $6 and every class dollars. For discrete features, like color or yes-no, this is again just counting frequencies within each class. How often is color red when the class is apple? For continuous features, like height, we often make another simplifying assumption, typically that the feature values within each class follow a Gaussian or normal distribution. So we just calculate the mean and standard deviation for that feature for all the examples belonging to each class. That's it for training.
Wow, okay, that does sound fast. And then, during the test phase, when a new example comes in, it just plugs the values into the formula, computes the posterior probability for every possible class, and picks the class with the highest score.
Exactly. For a new unseen test record of Math BFX, we compute that proportional score, PIC, for all possible classes. We then choose the class dollar that gives the highest score. This is known as the maximum a posteriori, MAP, decision rule. And it's important to note, we can often completely ignore the denominator in Bayes' theorem, the p-procedures part, because it's the same constant value for all the classes we're comparing. Since we only care about which class has the largest score, that constant denominator doesn't actually affect the final decision, we just compare the numerators.
Okay, this brings us to the really interesting contradiction, the paradox of naive Bayes. We know the independence assumption is often wrong. This means the algorithm frequently has low probability accuracy. The actual computed probability value, like 70% chance it's Class A, is often mathematically incorrect because the dependencies were ignored. Yet, we use naive Bayes all the time because it's often surprisingly accurate for the classification task itself. How can an algorithm be wrong about the probability number but still be right about which class to choose?
This is the real aha moment for understanding naive Bayes, and it brilliantly demonstrates the subtle difference between probability estimation and the task of classification. The classifier, using the MAP rule, only needs to know which class is the most probable. It doesn't actually require the absolute probability values themselves to be perfectly correct. It only needs those calculated probabilities, even if they're inaccurate, to be correctly ordered.
Can you give us a quick, concrete example of that?
Sure. Imagine a simple two-class problem, Class A and Class B. Let's say for a given data point, the true probability of it being Class A is 0.9, very likely, and Class B is 0.1, very unlikely. Now, because the naive Bayes model ignores some feature dependencies, it might incorrectly calculate the probability for Class A as, say, 0.7 and for Class B as 0.3. Notice both of those calculated probability values, 0.7 and 0.3, are mathematically wrong compared to the true probabilities, 0.9 and 0.1. The probability estimates are inaccurate. However, the classifier still ranks Class A with its calculated score of 0.7 higher than Class B with its score of 0.3. Since the MAP decision rule only cares about which score is highest, it still correctly chooses Class A. The ranking was preserved even though the values were off.
Ah, that's a huge insight. So the incredible efficiency and speed of naive Bayes come directly from making that simplifying naive assumption. And its surprising robustness in classification comes from the fact that often those real-world conditional dependencies might distort the magnitude of the calculated probabilities, but they do so roughly equally across the classes, so they don't usually change the final rank order.
Precisely. That's the magic trick. Training and testing are super efficient. It requires very little data to estimate the parameters it needs, just means standard deviations for continuous features, and simple counts for discrete ones. So while you probably shouldn't use naive Bayes if you need a highly reliable, calibrated estimate of the actual likelihood or probability of the class, it remains a fantastic, fast, and often highly effective classification tool, especially as a baseline or when speed and efficiency are absolutely critical.
Okay, and just quickly, when would the naive Bayes model likely fail completely, even on just getting the classification order right?
It would typically break down when the dependencies between features are so strong and perhaps interact in complex ways that ignoring them causes a complete reversal in the calculated probability ranking. For instance, if two features are very strongly dependent, maybe redundant, and the model treats them as independent, it might essentially double count their combined influence. This could artificially inflate the calculated score for a less likely class enough that it numerically surpasses the score calculated for the truly most likely class. That's when the naivete bites you and leads to a direct classification error.
Okay, this has been a fascinating exploration. We've covered three fundamentally distinct philosophies today: the local, instance-based knowledge of KNN, the consensus-driven, error-reducing power of ensembles, and the fast, probability-based shortcut of naive Bayes. Let's try and synthesize the biggest takeaways for the listener. What should they remember?
Yeah, I think the key is really understanding where each of these algorithms excels and, just as importantly, where it tends to fall short. They have very different strengths and weaknesses.
Okay, so first, KSNN. That's the adaptable lazy method. It seems perfect when you need a model that can incorporate new data instantly just by adding it, and it can handle complex, maybe nonlinear decision boundaries pretty well just based on local neighborhoods. But its efficiency, or rather lack thereof at prediction time, is its major downfall. Classification gets really slow for large data sets, and it becomes pretty much unusable in really high dimensions where data sparsity just destroys the meaning of distance metrics. And remember, as you said, that tell your due distance requires careful feature normalization beforehand.
Right. Then we have the decision tree ensembles. We saw that bagging primarily uses parallel strong learners, those big complex trees, mainly to reduce variance, effectively stabilizing those noisy decision boundaries you get with single complex trees. Then, random forest takes that a big step further. It dramatically improves on bagging by adding that crucial element of feature randomness at each split. This is specifically designed to prevent the base learners, the trees, from becoming highly correlated. The result is generally even lower generalization error, plus that very useful side benefit of getting feature importance estimates.
And boosting represents the sequential adaptive approach. It typically uses weak learners, like shallow trees or stumps, and iteratively focuses its computational effort squarely on correcting the errors made by the preceding models in the sequence. The main goal here is typically bias reduction. So the takeaway for Ensemble seems to be, if maximum predictive accuracy is your absolute top priority, and you can afford the computational expense and potentially the loss of interpretability, exploring an ensemble method, especially maybe a well-tuned boosting model like gradient boosting or XGBoost, is usually going to be a very strong contender, maybe even the right answer for many practical problems.
Absolutely. Ensembles should be in your toolkit for almost any serious classification task. Finally, we have naive Bayes. It offers incredible speed and efficiency, both in training and prediction. Its foundational flaw, that naive independence assumption, means its calculated probability scores are often inaccurate in absolute terms. But its classification performance is surprisingly often salvaged by the MAP decision rule, which only requires the relative ranking of the classes to be correct, not the precise mathematical probability values. It remains a fantastic baseline classifier, especially when efficiency is paramount or as a starting point.
Now, here is where it gets really, really interesting. Connecting these classic techniques, some of which have been around for decades, to the cutting edge of machine learning today.
Yeah, it's fascinating because the core principles we've discussed today, particularly the power of diversity and aggregation found in ensembles, are absolutely fundamental and timeless. The sources we looked at confirm that modern researchers are applying these exact ensemble philosophies, especially ideas from boosting and bagging, directly to deep learning models. They train diverse collections of deep neural networks, maybe varying the network architectures, using different hyperparameter settings, different training techniques, or different subsets of data, and then they combine these diverse, accurate, deep classifiers to create deep ensembles. And these often achieve state-of-the-art accuracy on really complex benchmarks, showing that the power of combining models really transcends the specific underlying methodology, whether it's decision trees or deep networks.
That's really cool. So if the concept of imposing structure, forcing correction, like we see in random forest and boosting, yields such high returns in accuracy, let's leave our listener with a final provocative thought that actually loops back to the very beginning. KNN.
Right. We talked about KNN's potential utility stemming partly from its extreme laziness, the intriguing fact that the model is simply the raw, stored data itself, requiring essentially no structured training time up front. Now, think about the context today. We have massive computational power readily available. Cloud computing makes scaling easier. Large, complex ensemble models like random forests or gradient boosting machines can be trained relatively quickly. And memory storage for holding vast amounts of data is cheaper than ever. So the question is, how does the utility of that lazy learning philosophy really change in this modern era? When is the truly modelless approach, just relying on the raw data and a similarity distance calculation performed at query time, genuinely superior to the highly structured, error-correcting, variance-reducing frameworks that we deliberately impose in advanced ensembles? Is there still a critical niche, perhaps in specific types of problems or data domains, where simply storing the data and measuring distance to find neighbors is, in fact, the optimal, most effective design choice, despite its computational cost at prediction time? Or has the sheer power and efficiency of structured learning and ensembles largely surpassed the need for that kind of extreme laziness?
Hmm, definitely food for thought. When is lazy still the way to go? Thank you for joining us for this deep dive into classification algorithms. We'll see you next time.